Welcome to this week's Short Clip Friday podcast. Each Friday, I'll be posting 10 to 15 minute segments from previous podcasts. And the point here is just to bring you some of the highest yield topics from each podcast in order to kind of reinforce those topics. This clip is from the Acids and Bases podcast and covers some of the general definitions of acids and bases. Enjoy. So the first thing I want to start with is some of the basic definitions of acids and bases. So the first definition was put out by Arrhenius, and he defined an acid as any species that increased the concentration of hydrogen ions in aqueous solution. And on the flip side of that is the Arrhenius base, which is any species that increases the concentration of hydroxide, which is OH minus, in aqueous solution. Then along came Bronsted, who was a chemical engineer, and his friend Lowry, who was a physical chemist, and they came up with the idea of a Bronsted-Lowry acid and base. And so a Bronsted-Lowry acid is a proton donor, or an H plus donor, and a Bronsted-Lowry base is a proton acceptor. It accepts protons. And so you can see this obviously in water. Water can either act as a Bronsted-Lowry acid or base. If it is accepting a proton, it can accept a proton and turn into hydronium, H3O plus, and then it can donate that proton away. So when it accepts that hydrogen, it's a base. But when it's a hydronium ion and it's giving that hydrogen away to become H2O, water, it becomes a acid. And then the next definition, also the kind of most complex or kind of difficult to understand and difficult to see straight up, is the concept of a Lewis acid and a Lewis base. So a Lewis acid is defined as an electron pair acceptor, and a Lewis base is defined as an electron pair donor. So if you remember in organic chemistry, you can have pairs of electrons attack or pairs of electrons be basically accepted. You can have electrophiles and nucleophiles. A nucleophile is a reactant that provides a pair of electrons to form a new covalent bond, and a electrophile is the opposite. It is a species that accepts a pair of electrons to form a new covalent bond. And so if a pair of electrons attacks some atom, that would be a Lewis acid-base reaction. For the sake of an example, let's say you have ammonia, which is NH3, and it's got a lone pair of electrons, and it attacks boron trifluoride. And so these electrons that are the lone pair on the nitrogen of ammonia attack the boron, which is the electron acceptor. And so you could say the nitrogen, which is donating those electrons, is the Lewis base, and the boron, which is accepting those electrons, is the Lewis acid. And it's important here to note that that a Lewis acid-base reaction does not need to include the transfer of a proton. So that's something to look for. I'm sure I do this as well, but you think, okay, it asks me, is this an acid-base reaction? Well, there's no transfer of a hydrogen ion. Of course not. Well, that's not always the case. Remember to make sure that there's no transfer of an electron pair before answering the question no, because there might be. So one useful thing then is to understand how to recognize Lewis acids or bases just kind of by looking at them without tracking electrons. What in a compound should make you think, okay, this might be a Lewis acid? All right, so with Lewis acids, and remember these are electrophiles, there are two things that you should recognize that will make you think, okay, this might be a Lewis acid. And that's number one, a compound that has less than 8 valence electrons. So this is going to be something, and again, this is where the central atom has less than 8 valence electrons. So this is going to be something like boron trifluoride. And then the second thing you want to notice is a compound in which the central atom is capable of expanding their valence shell
beyond 8. So this is something like phosphorus pentachloride, which is PCl5, or SF4, something with a bunch of bonds. You want to look at that and say, okay, that is expanded beyond its 8 valence. It's 8 valence electrons. That is possibly a Lewis acid. And then for Lewis bases, remember these are nucleophiles. And these are a lot easier. You just want to basically look for a lone pair of electrons, and that should tell you, okay, this thing is probably a Lewis base.
And lastly, a Lewis acid-base reaction forms a Lewis adduct, which is just the product of a Lewis acid and base reaction. All right, moving on. Let's talk a little bit about the definitions of strong and weak acids. So what is a strong acid? So a strong acid is something that completely disassociates. And what I mean by disassociates,
I mean that this acid dissolves in solution and that there's no more of the protonated form of this acid. Instead, you are left with just conjugate acid and conjugate base. So for example,
HBr, which is hydrobromic acid, a strong acid completely dissociates, so then you have all hydrogen ions and all bromine ions as it disassociates. And so there are 6 of the strong acids to know for the MCAT. These are hydroiodic acid, which is HI, hydrobromic acid, which is HBr, hydrochloric acid, which is HCl, perchloric acid, which is HClO4, sulfuric acid, which is H2SO4, and nitric acid, which is HNO3. And so you can remember that the first 3 at least, I, B, Br, and Cl, are all halogens on the periodic table, which is the furthest column to the right. So as I'll talk about a little bit later, the strong acids and bases are the easiest to do calculations for and are the easiest to figure out titration curves for, etc. That's really what you want to be working with. Of course, that's not always the case, but those make for easy calculations. And so moving on to a strong base, in the same way, a strong base completely ionizes to fully form its conjugate acid and leaves none of that base in solution. And so an example of this is a metal hydroxide. So let's take lithium hydroxide, which is LiOH. And so it fully disassociates into a lithium ion and a hydroxide ion, which makes it a strong base. And then, as you could probably guess, or as you probably know, the weak acids and bases do not fully ionize or dissociate in water. There's still some of that original acid or base left in solution at equilibrium. If time were to go to infinity and you let it just sit there forever, it's not all going to dissolve. It's going to sit with some of that acid still left. And so an example of this is acetic acid, which is the acid component of vinegar. And so only about 0.4% of the acetic acid that's in solution actually disassociates. So that makes it, 99.6% of acetic acid in solution is still in that protonated form. It doesn't give up its proton. And that's an example of a weak acid, a weak base, however less common, you still need to be familiar with. And one of these is ammonia. Ammonia in water, in aqueous phase, disassociates into NH4, which is called ammonium, and basically takes a proton from water, so it produces OH minus. And again, only a very small percent of these actually disassociate, and it's around like 1%, plus or minus 0.5% of these actually disassociate. So it's a very small fraction.